Heating and cooling curves. So these are graphs that we can use to represent their temperature versus time, graphs to represent the phase transitions between these things. These are important to know and useful. Um, yeah, we're seeing time increasing and then the temperature increasing, right? So the temperature is increasing over time. We reach the melting point right here at this plateau. It takes some time for the solid to fully melt, become a liquid, and then that liquid heats up and up and up till it reaches its boiling point, right? Again, it takes time for it to boil and evaporate, and then it becomes a gas, and you can heat it up some more. There's also cooling curves, right? It's the same idea, just in reverse. You're taking heat away, right? So the gas condenses, the liquid freezes to become solid. My question for you is why do the temperature plateau temperatures yeah, why do the temperatures plateau when a phase change occurs? So think about that. Maybe I can go back here. Think about why that happens. Take a second. Maybe pause the video. You can see these plateaus, right? And write your answer down in your notebook. I'll give you a second. Okay, why do temperatures plateau when a phase change occurs? So we're thinking about energy, right? Heat is energy, and we know that particles are moving, they have kinetic energy, right? So maybe let's go here. It's a little easier to think about this way. So we have a solid, we're giving it energy in the form of heat. When we get to the melting part, temperature plateaus, we're still giving it heat energy, right? But instead of that heat energy turning into a greater temperature of our solid, which the temperature, right, is a measurement of the average kinetic energy of all of your particles. Um, that energy is going to breaking apart the lattice bonds, right? The bonds that are making this solid. So that instead of increasing the average kinetic energy of our system, that energy is being used to break bonds so that it can become a liquid. So this whole process, we don't increase the temperature because bonds are breaking. Like, let's say this is water. This is all happening at 0 degrees Celsius. And it's not until all those bonds have broken that the temperature begins to increase because that energy is then going back to increasing the average kinetic energy of our system. A secondary question is why is this plateau bigger than this plateau? The answer is it takes a lot more energy for the liquid particles to become gas than it does for the solid particles to become liquid. That is because they have to fully overcome those intermolecular forces, right? Because a liquid is still experiencing those. They're moving past each other, but the intermolecular forces are keeping them close together. To fully overcome them, it takes a lot of energy. So you need to know those things, right? Okay, so another thing, effects of temperature and pressure. So as the temperature of a gas increases, particles gain more kinetic energy, right? Inverse is true for a decrease. We kind of just talked about this. The particles collide more frequently and with greater force. They have more kinetic energy, more motion, and so they will smash into each other more often and harder, right? Um, Imagine you're in a room full of people and you're just walking around blindly, and you're smashing into each other every once in a while, and then I tell you to run, right? That would be like increasing the temperature. You have more kinetic energy. You would smash into people much more, right? So the particles will spread out if they can to maintain a constant pressure, which means the volume increases, right? So temperature goes up, volume goes up. An increase in pressure forces gas particles closer together. So the same number of gas particles occupy less space, volume decreases. So if you increase the pressure, everything has to get closer together, right? Um, and they're gonna occupy less volume, and so, oops, sorry about that. They're gonna smash together more often, right? If they have less volume. Okay, let's talk about diffusion. This is part 2. So diffusion is when you have this concentrated amount of particles, and over time it gets evenly distributed until it becomes, or you get an equilibrium, which means it's evenly distributed in this case. So the random movement of particles from an area of high concentration to low concentration. So that's kind of illustrated right here. This is high concentration, right? A lot of them all bunched together. This is low concentration. And the particles in matter are in constant motion, right? They have kinetic energy. This happens in a gas or liquid because they're moving randomly and colliding. And then the collisions are more frequent in high concentration areas. The particles exchange energy and spread out, and then the diffusion continues until the equilibrium is reached, right? So this is like, you can imagine you have a glass of water and you drop some food coloring into it, and you can see all the particles at first like flowing into the water, and then eventually the water becomes fully that color because they become evenly distributed, right? And this has to do with entropy as well. Oh yeah, here's a picture of it. So the dye is added to the flask on the left and diffuses, it spreads out throughout the water. If it's left long enough, the concentration of dye will be the same everywhere. That would be equilibrium, and the color of the liquid will be uniform, right? So diffusion takes time. Different things can diffuse at different speeds, right? I'm going to ask you a question about that in a second. But diffusion is the spreading out of highly concentrated areas until you reach equilibrium. So, here's my question. Will helium gas or oxygen diffuse quicker within a given container? And I gave you a hint. Helium has an atomic mass of 4.003 AMU, and oxygen has an atomic mass of 15.999. So take a second. In your notebook, write down what you think the answer is, and then I'll let you know. So, the answer is helium will diffuse much quicker. And that is because it is much lighter, right? It has an atomic mass of 4.0026. Oxygen has an atomic mass of 15.9994. And actually, gaseous oxygen is 2 oxygens put together, so it's more like 32. Right, but this is much heavier, so it takes more energy to move, which means it will have a slower rate of diffusion. So the lighter thing will diffuse more quickly than the heavier thing, right? Okay, that is chapter 1. That is our revision. I'm going to have you answer some questions about that, and I want to see where you're at with all that. All right, good luck.